This video is the first in a series in which we're going to study the thermodynamics of mixtures. Our work in the prior videos was concentrated on looking at the stability of pure substances, right? So that was just restrained to phase equilibrium. Now we're going to have mixtures where you have more than one component. And the goal then is going to be to see if we can understand how thermodynamics predicts the stability of those mixtures of more than one component. It's pretty obvious to estimate that the properties of those mixtures will depend on the relative amounts of the components. So it's imperative to have a good understanding for how to specify the relative amounts of those components. Now, most of the time we're going to be looking at binary mixtures, and those are mixtures of only two components. So most of the time you will have that one component will be majority, and we will call that the solvent, and the other component will be minority, and that will be the solute, right? So in this video we're simply going to talk about the common ways that we have to express the relative amounts of those two components in a binary mixture. We're going to separate our work between gases and liquid mixtures, because those are going to be the two main cases we're going to be looking at. So for gases, this will be a review because we have already seen many of these measures of concentrations before. The best way to express the relative amount of two components in a mixture of two gases would be using the mole fraction. Right, so the mole fraction is simply x sub j will be the number of moles of that component j over the total number of moles in the mixture. Right, so if you have two components, j and I, then there will be number of moles of j plus number of moles of I. And again, this is a really good descriptor for the relative concentrations. It actually gives you a direct indication of how many particles of one gas you have with respect to the other. Okay, but there's more measures of concentration that are useful for gases. You can also use partial pressures. Right? So if you have a mixture of, say, of two gases, the total pressure of the mixture is simply going to be equal to the partial pressure of each one of the components, A and B. Right? So this is Dalton's law, in essence, and these partial pressures are also useful. Now remember that partial pressures can also be used to express mole fraction. Right? For ideal gases, what we can say is that this mole fraction, x to j, is also the ratio of the partial pressure of the gas of interest divided over the total pressure of the mixture P tot. Okay, where this is just the sum of the various components that you have. All right, so that is for gases. Again, mole fraction, partial pressures, either one of those two works well. What about when you have mixtures in solution, right? So liquid mixtures. How do you express the relative amounts of the components in the mixture? Well, for liquids, we can also use mole fractions, and we will use them when we actually start to derive the formalism of thermodynamics for liquid mixtures. Right, so the same thing applies, right? Here you will have that the mole fraction of a component in a mixture is going to be equal to the moles of that component over the total number of moles. Right, notice that in this case we're not going to have a definition of the mole fraction using partial pressures, because there's no partial pressures that really tell you what the relative amounts are for a liquid. Okay, that's much more for a gas. All right, so again, this is still going to work well, and notice that the symbols are the same for a gas and a liquid. So if we have problems in which we have to talk about the mole fractions of gases and liquids, we'll have to be very careful about how we denote when we're talking about the mole fraction of a gas or the mole fraction of a liquid. Okay, great. So the mole fraction works well for a liquid, but there's other measures of concentration that are far more common. Perhaps the most common would be molarity, okay, or molar concentration. So molarity usually is expressed with brackets for component J, and that is simply the number of moles of J over the volume of the solution. Now, the units of this molar concentration are typically mole per liter, which we call molar, or capital M, right? So this capital M, usually when you have a concentration of, say, 0.1 molar or 1 molar, that means mole per liter. But notice that that molar concentration actually is not directly in the SI system. So if you have to use molar concentrations in problems where you might have constants like R that you're going to be using SI units for, then the units that we're going to have for the molar concentration will be mole per cubic meter instead. And that's fairly uncommon to use because we're kind of wired to use this capital M molar as mole per liter. And again, there will be cases in which we need to use that in moles per cubic meter. Okay, so that is one very common way to express concentration in liquid mixtures. But there's others. There's molality, not molarity, but molality, which I'm going to write using a subscript B. Okay, so the molality of J is simply the number of moles of J divided by the mass of the solvent. Okay, so generally this is, we use a symbol M, lowercase m, which I don't particularly like because it can be confused with mass, but M is used for molality. And in the SI system that is going to be moles per kilogram of solvent. Okay, so molarity, molality. Now, generally in chemistry we like to use this one. Okay, but this one has an advantage over that one, and that is that this one is independent of the conditions, right? You can clearly see how the temperature will affect the value of the concentration because the volume, the density of a substance changes with temperature. It also changes with pressure. Okay, but molality is simply moles over mass, and both of those quantities are temperature and pressure independent, right? So if you want to do really accurate work, then molality will be preferred. There's one final unit of concentration that we're going to talk about in terms of liquids, and that is going to be mass concentration, which I'm going to use a symbol C of J. Okay, and this is going to be simply the mass of the solute, mass of J, over the volume of the solution. Okay, and the units would be grams per liter, or if you actually want to use SI units, would be kilograms per cubic meter. Okay, this one is useful whenever you're trying to handle substances for which you might not have a molar mass, right? So for example, think about macromolecules like a polymer. Sometimes we actually, when we make a polymer in the laboratory, we don't know very well what is the molar mass of that polymer. So that means that we can't have either molarity or molality or mole fraction, right? But still you like to make solutions, right? So what you simply say is, well, I have a solution that is 10 grams of this polymer per liter of solvent, right? So that works well. It also works well for biomolecules. When you have proteins or molecules that are very large and where the molar mass might be a little awkward to use, you simply say, I'm going to make a protein solution with 10 grams of the protein per liter of solvent. All right, so in this video we have reviewed the main measures of concentration that we will be using to determine the relative amounts of components in mixtures. In the next videos we're going to begin with the formulation of the thermodynamics of mixtures.